Tuesday, how it's related to logarithm argument and the rest of the story in this chapter. So to this end, let's recall what we're doing. So recall. By the way, is there supposed to be more light like this? Oh, you're better without them? But whatever you think. So we talked about covering. So these are maps phi of, say, topological spaces, but for us these are either subsets of a line or subsets of complex plane. So surjective maps continuous with these two conditions, that preimage of any point is discrete in Y. So like we should imagine a countable collection, or no more than countable collection of points, which are don't have accumulation point. And second, for every x in X, there exists a neighborhood U, which is U of X open, such that its free image is isomorphic to disjoint union of elements in the preimage of the point of the same neighborhood. So when I write this, I mean homeomorphic, so isomorphic in this world of continuous maps. In these stories, we suppose that X is path connected. So among these coverings, we introduced the universal covering, of X, pi X tilde to X, which means two things. First of all, X tilde is, well, it's a covering, but also X tilde is connected, and X tilde is simply connected. So for example, if we have a line and then over it two lines, each of them projecting to this line, it's not an example of universal covering because this is not a connected space. So that's where it's used that X tilde is connected. Okay, and then we stated that universal covering exists and is unique. And the examples we considered if X is simply connected, then X tilde simply equals X, and this covers X equals real line, positive part of real line, X equals to complex plane, X equals to any star-shaped subset in a complex plane. Also, we had these two basic examples. So, real line covers unit circle, and this is universal covering. Delta goes to cosine of And secondly, the basic one, C to C star, given by, say, exponential function. Very good. Now let's continue. So we also talked about sections. Of covering. So these are maps, so defined on some U in X, usually open, so on some subset. These are maps, continuous maps S from U to Y, with the property that pi composed with S is identity. So continuous. Yes. And then our final topic was about lifting paths and path homotopes. So this is crucial for this story, and that's what we'll use today. So I'll repeat the statement without proof. Although when I write it down, I'll mention what this proof uses from the book, for example, or what statements from the book look exactly like the proof here. So the theorem I stated was like this. Let A, so let's have a covering. And suppose we have a path gamma in X, 0, 1, or in B, it doesn't matter. So whenever we talk about coverings, we suppose that X is path connected. So it's a path, and X0 is just gamma of 0. So we pick its preimage. Then there exists a unique path gamma tilde from 0, 1 to Y with two properties. Gamma tilde of 0 is Y0, so it starts at Y0. And also pi composed with gamma tilde is gamma. So and B, if we have a pair of such paths, so let gamma 1, gamma 2 be paths in X. So gamma 1 of 0 equals gamma 2 of 0, gamma 1 of 1 equals gamma 2 of 1, and moreover they are homotopic. So they are path homotopic. To gamma 2. And let's say that Y0 again is preimage is in Y, pi of Y0 is at 0. Then the lifts which exist by A, gamma 1 tilde and gamma 2 tilde with gamma 1 tilde of 0 equal gamma 2 tilde of 0 equal Y0 are also homotopic. this is extremely important. For example, because corollary for such gamma 1 tilde and gamma 2 tilde, in particular we have gamma 1 tilde of 1 equals gamma 2 tilde of 1. So the endpoints are completely defined by, so let me reformulate it. So the endpoints of lifts of paths depend only on two data. So first, starting point, and second, homotopy class of path. Of path gamma below. So this will be used today. Let me keep it on the blackboard. So, so here is the example of this, which, under completely different names, is in the book. It's called argument function. So let's see. We have complex numbers and exponential function 2c star. And also, let's consider the projection from complex numbers to real numbers called taking imaginary part, and the embedding, which I call I, which is embedding the imaginary part. Okay? So, so here is our complex number. So maybe let's talk about some subset U, or maybe not even U, but A, because it doesn't need to be open. Now let me tell you the definition. And so there are many of these. An argument function I'll call it arg A. It's a function defined in A with values in R. So we go with this. It's a function which is continuous. And such that for every A in A divided by absolute value of A equals, so we apply argument, then we apply imaginary embedding and apply exponent. So is exponent of I argument of A. In other words, this is sine of I of argument of A plus I sine if you open up the book, it's beginning of section 2, you'll see that my definition exactly copies their definition. So I just drew this wonderful picture, but this formula is exactly the one from the book. Now, here is my claim. So let's first formulate a general claim. Maybe. Suppose we have some covering. And suppose U in X is simply connected. And O. Restrict the covering. So denote why U is just pre-image of U. So we know already that phi restricted to U is a covering as well. Now it has a section. There exists a section S U to Y U of phi restricted to U. So whenever we restrict ourselves to a simply connected subset, any covering has a section. So let me prove it. So there are two observations. First, U is simply connected. Thus, its universal covering coincides with U itself. This was our basically definition of universal covering. It's a simply connected covering. Now let's use universality. So we have this YU and then U tilde. Both are coverings of U. But this is actually an equality. Now universality says that there is a map like this. So this is pi U. So call this map S. So by universal property of U tilde, which in our case coincides with U, there exists S, which goes from U equal U tilde to YU, satisfying the condition that going like this is going like this. So phi U composed with S is, but this is just identity. And then it's a section. So this is a definition of a section. Okay, so this was general. Now I'll apply this lemma to our situation. Corollary, which will appear many times today. So let U in C star be simply connected. For example, U is a disk, which totally sits inside C star. Oh, C star, I think you should get used to it. It's C without zero. So it's very typical. C star, C without zero. Then there exists a continuous section S from U to complex numbers with exponent of S of Z equal Z for any Z in U. So I'm not calling this logarithm because this function is not holomorphic at this point, it's continuous. Later we'll see that this S is bound to be holomorphic, but that's a different story. We'll discuss it later. Right now we will use it for corollary of corollary. So is it clear how to use how to derive corollary from the lemma? Right? Because we had the universal covering. C covers C star, and then basically I apply the lemma. Good. So now corollary from corollary. Let U and C without zero be simply connected. And then, well, let me draw this picture. C without zero, exponential map. Also, I will have this U here, and we constructed this section. And we have this real line which connects to C by imaginary part and imaginary embedding. So I claim that if we go like this, so then imaginary part of S, which is a map from U to real line, is an argument function on U. So choosing a section defines an argument function. So let's see. So this. So what do we need to check? We need to check that so I prove. So let's take Z in U. We need that if we apply exponential function to this arg U of A of Z, and then divide it by and then divide it by absolute value of Z. Sorry, not multiply it by absolute value of Z. Then this is Z. So this is what we need to check. Okay? So I need to check. Well, this becomes easy. So so by definition of section, exponent applied to S of Z is Z. On the other hand, this is exponent applied to real part of S of Z plus I imaginary part of S of Z. Which is a product times this yeah, I should write here I. Sorry about it. It's cosine and sine, so I is there. Yeah. So we see that this part is exactly x I R U of Z, and this, of course, if you think about it, what this is complex number of absolute value 1. And then this is, and this is a real number, then this real number is bound to be absolute value of Z. Because this is in S1, and this is in R. And there's a unique presentation of complex number in polar coordinates. Right? So if you have some presentation of a complex number as a product of a real number, positive real number, and a point on S1, so a complex number of absolute value 1, then this is bound to be the absolute value. So this is outcome is that Z equals absolute value of Z times exponential function applied to I argument of Z. So get what we wanted. Z is argument of Z times exponential function. So not argument, but absolute value of Z times exponential function. So in particular, as I stated, this works for any star-shaped domain. G inside C without 0. And a typical choice is like this. You can, a typical choice. So we need to take a subset, an open subset in C without 0. Then you can, so this is not star-shaped, it's not even simply connected, but to make it star-shaped, we can throw away one ray starting from 0. So you can throw away any ray in the direction alpha. So a typical choice is like this. So one can argue the function. Exists for any, so for G equal let's say C without this ray, I'll call it probably R alpha. This is R alpha. So alpha is the direction. Such domains have their own notations. They're called C sub alpha. So in particular, so this is a notation. So in particular, standard choice is this. So this is C sub pi. Argument functions exist. So actually, they exist. There are many of them, and it's important. So it's a remark. So suppose this argument function exists for u and c without 0, so u is simply connected. Then, so choose one. Exists means that there exists at least one, so take one. Take such. Call it as u. And then goes to u of z. Then another one, arg u plus 2 pi n. So z goes to arg u of z plus 2 pi n is another argument function. So this is like a constant. Now this is completely clear because indeed exponential of 2 pi ni equals to 1, so we just don't notice this. And actually the other way around is also true. If you have two argument functions, arg prime u, arg double prime u, are two argument functions, on u simply connected, then their difference is a constant function. For some n. So it's a statement which I think I'll just keep as an exercise. It's proved in the book, but it's easy. Good. We have talked about argument functions defined on simply connected subsets, but there's another related issue. Argument functions on a path. I claim let gamma from say 0, 1 to C star, C without 0, be a path so gamma star, so take A equal gamma star, it's a subset in C without 0, then argument function on A exists. Let me prove it, and I'll derive it from this lifting of paths. So a remark. In view of what I've chosen to be standard statements, the proof is very elementary. So we will derive this from lifting of paths. Let's see. So, proof. So let's consider C and then exponential function to C star. Oh, sorry, C without 0. And we have a map from 0, 1 to C without 0, called gamma. Now, since it's a covering, let's choose, choose some starting point. So gamma of 0 is x0, and y0 is in C, exponential of y0 is x0. So here we have x0. Then we remember, then by the theorem, there exists a unique path gamma tilde from 0, 1 to C with, in our terms, exponential of gamma tilde of t equal to gamma of t. T is in 0, 1. Such path is unique. Now, maybe here. Let's look at this condition. So, exponential of gamma tilde equals gamma means of t. So, this means that if z is gamma of t, then gamma tilde of t can be chosen as section of z. So we have a section of this covering on, so we get a section of exponential function. defined on the image of gamma. But if you have this section, so then you just can put argument gamma of z to be equal to imaginary part of this section. So imaginary part of gamma tilde of t, where z is gamma of t. So the important thing is that this path upstairs is unique. So now my final observation is that if you look at if you compare this to what is the proof in the book, which is I'll tell you what. It's theorem 5.10. So comparing this with the proof from the book, we see that actually we're using the same strategy. So the strategy in the book is like this. We have this path, gamma of 0, gamma of 1, cover this path by finitely many disks, which are small enough. So cover gamma star by finitely many disks in C without 0. Construct an argument function in each disk, and then glue them together into one argument function. So this is the strategy from the book. Now, I didn't talk in detail on Tuesday about this lifting construction proof, but lifting of gamma was constructed similarly. Namely, again, cover the image of gamma by finitely many disks. Then each of these disks, by the property of covering, has a copy inside the covering space for us above the exponential map in C. So lift each disk. To C. So then, thus, lift the part of gamma tilde, gamma star intersect with the disk to C, and then so we have many liftings, and then we glue them together. And then glue. So I think that in principle, on Tuesday I thought that this part goes without proof, or goes only with a hint of a proof. But if you're interested, looking at what's written in the book about the construction of this argument function, this little disks construction and then gluing, you can try to recover a complete proof of the existence of this lifting of the path. So if you're interested in this, you can do this. This is a standard statement in all books about this kind of topology. It's proved. But the point is that the proof from the book, it just copies this proof in one particular case, which we need for existence of argument function. So I think that even though it looks more complicated when you go it abstractly, but trust my experience, I talked with many people who learned this story, and I learned this story myself when I was a student. Until you accept this picture with coverings, you cannot understand what these functions actually are, what's going on. So, I mean, these equations, they don't make sense. But when you think about this as sections of the covering, it really, really is in your head. So please pay attention. Of course, it doesn't help in calculational problems, but that's a different story. Good. Let's have a break. Those who haven't put their